Picture yourself standing beneath the vast Hawaiian sky on the night of October 19th, 2017. The air carries that particular crispness that comes with altitude, here at the Haleakala Observatory on the island of Maui, where the night sky reveals itself in ways that most of humanity never experiences. The Milky Way stretches overhead like a river of light, and the stars shine with an intensity that seems almost impossible to those accustomed to city lights. This is where our story begins, in the darkness of a Hawaiian night, with an astronomer named Robert Werrick sitting at a computer screen, reviewing data from the Pan-STARRS telescope system. The Panoramic Survey Telescope and Rapid Response System, known as Pan-STARRS, represents one of humanity's most ambitious attempts to catalogue and monitor the ever-changing canvas of our night sky. This remarkable system consists of wide-field telescopes equipped with the world's largest digital cameras, each containing approximately 1.4 billion pixels. These electronic eyes scan the heavens methodically, capturing images of vast swathes of sky multiple times each month, searching for anything that moves against the backdrop of distant stars. Robert Werrick wasn't looking for anything extraordinary that night. His work involved the routine but crucial task of identifying near-Earth objects, asteroids and comets, that might pose a potential threat to our planet. This work requires patience, dedication, and a keen eye for detail. Every night, the Pan-STARRS system generates an enormous amount of data, terabytes of information that must be carefully analysed. Most of what the telescope finds consists of known objects following predictable paths, or new discoveries that fit neatly into our understanding of the solar system's population of small bodies. The process of discovery in modern astronomy rarely resembles the romantic image of a lone observer peering through an eyepiece and exclaiming in wonder. Instead, it involves sophisticated software algorithms processing digital images, comparing them to previous observations, calculating trajectories, and flagging anything unusual for human review. The Pan-STARRS system had been operational for several years by that October night, and its routines were well established. The telescope would capture images of the same regions of sky at different times, and software would identify objects that had moved between exposures. As Werrick reviewed the data from observations taken on October 19th, something unusual caught his attention. There was an object moving through the field of view, which itself wasn't remarkable. What made this object stand out was its motion. It was moving fast, unusually fast, and its trajectory didn't match anything in the database of known solar system objects. The software had flagged it as potentially interesting, and now Werrick's trained eye confirmed that this warranted closer examination. The initial observations showed a point of light, indistinguishable from a star except for its motion across the sky. The object was faint, about 21st magnitude, which means it was about 400,000 times fainter than what the human eye can see on the darkest night. Only our most powerful telescopes could detect such a dim object, and even then it appeared as nothing more than a few pixels of light against the cosmic dark. Werrick's first task was to determine whether this might be a known object that had somehow been missed by the automated identification systems. He checked the Minor Planet Center's database, the global clearinghouse for observations of asteroids and comets. Nothing matched. He examined the object's apparent motion more carefully, calculating preliminary orbital parameters. The numbers that emerged from these calculations were extraordinary. The object's velocity was the first indication that astronomers had discovered something unprecedented. It was moving at approximately 26 kilometers per second relative to the Sun, far faster than the typical speeds of asteroids or comets originating within our solar system. But velocity alone doesn't tell the whole story. What matters in celestial mechanics is the object's total energy, the combination of its kinetic energy from motion and its gravitational potential energy from its position in the Sun's gravitational field. When Werik calculated the object's orbital eccentricity, a measure of how elongated its path around the Sun would be, he found a value greater than 1. In the language of orbital dynamics, this meant the object was on a hyperbolic trajectory. Unlike the closed elliptical orbits that keep planets, asteroids, and comets bound to our Sun, a hyperbolic path meant this object was just passing through. It had come from interstellar space and would return there after its brief encounter with our solar system. The realization of what they had found began to sink in gradually. This wasn't just another asteroid or comet. This was humanity's first confirmed detection of an object that had originated in another star system. For decades, astronomers had theorized that such objects must exist, that the space between stars should contain a population of wanderers expelled from their home systems by gravitational interactions. But despite years of searching, none had ever been conclusively identified until that October night. Werik immediately recognized the significance of the discovery and initiated the protocols for confirming and announcing the finding. Additional observations were crucial. A single night's data could contain errors, and extraordinary claims require extraordinary evidence. He contacted other observatories, alerting them to the presence of this unusual object and requesting follow-up observations. The astronomical community responds quickly to such requests, understanding that time is often critical when observing transient phenomena. The Catalina Sky Survey in Arizona had actually imaged the object a day earlier, on October 18th, but their automated systems hadn't flagged it as unusual. Once alerted to its presence, astronomers were able to find the object in their archival data, providing additional observations that helped refine the orbital calculations. These pre-discovery observations proved invaluable, extending the arc of observations and allowing for more precise determination of the object's path. As news of the discovery spread through the astronomical community over the following days, telescopes around the world turned toward this mysterious visitor. The European Southern Observatory's Very Large Telescope in Chile, the Gemini Observatory, the Canada-France-Hawaii Telescope, and many others joined the observation campaign. Each telescope brought different capabilities to bear, from high-resolution imaging to spectroscopic analysis that could reveal the object's composition. The challenge facing astronomers was significant. The object was already moving away from Earth and the Sun, growing fainter with each passing day. Its high velocity meant that the window for detailed observations would be limited. Unlike comets or asteroids that orbit the Sun and can be observed over multiple passes, this interstellar visitor would offer only one opportunity for study before it disappeared forever into the cosmic dark. The early observations revealed puzzling characteristics that would only deepen the mystery in the weeks to come. The object showed no signs of a coma or tail, the cloud of gas and dust that typically surrounds comets as they approach the Sun. This suggested it might be an asteroid, a rocky or metallic body rather than an icy comet. But its behaviour would soon challenge even this basic classification. The brightness of the object varied dramatically as it rotated, with a periodicity of about 7 to 8 hours. This variation was extreme, suggesting that the object was highly elongated, perhaps 10 times longer than it was wide. No asteroid or comet in our solar system shows such an extreme shape. The brightness variation suggested something shaped more like a cigar or perhaps a pancake, tumbling through space in a complex rotation. These initial observations also revealed that the object had already made its closest approach to the Sun on September 9th, about 40 days before its discovery. It had passed within about 37 million kilometres of our star, closer than Mercury's orbit, and was now heading back out into interstellar space. The fact that it had survived such a close solar approach without showing cometary activity was itself remarkable, suggesting either an unusual composition or that any volatile materials on its surface had long ago been stripped away during its interstellar journey. The Discovery team worked through the night and into the following days, gathering data and preparing their announcements. The International Astronomical Union, the organisation responsible for naming celestial objects, would need to be notified. The Minor Planets Centre would issue a formal announcement. Scientific papers would need to be written and submitted for peer review. But even as these formal processes began, the astronomical community was already buzzing with excitement. Word of the discovery spread beyond professional astronomers to the wider scientific community and the public. Here was something that captured imaginations in a way that few astronomical discoveries do. This wasn't just another distant galaxy or exoplanet, statistics to add to our catalogues. This was a visitor from another star system, a tangible piece of another solar system that had wandered into ours. It represented a bridge between our cosmic neighbourhood and the vast expanse of interstellar space. The timing of the discovery was fortuitous in many ways. Had the object arrived a few decades earlier, our telescopes might not have been sensitive enough to detect it. Had it followed a slightly different trajectory, it might have passed through our solar system unnoticed. The Pan-STARRS system, specifically designed to detect moving objects, was ideally suited for this discovery. The digital revolution in astronomy, with its automated surveys and sophisticated data processing, had made it possible to find this needle in the cosmic haystack. As that first night of confirmed discovery gave way to dawn over Haleakala, Robert Sweryk and his colleagues knew they had made history. They had found humanity's first confirmed interstellar visitor, an object that had travelled between the stars to briefly grace our solar system with its presence. But they could not have imagined the debates, controversies and mysteries that would surround this object in the months and years to come. The discovery was just the beginning of a story that would challenge our understanding of planetary systems, raise profound questions about the nature of interstellar objects, and even spark serious scientific discussion about the possibility of artificial origins. The days immediately following the discovery of the interstellar object were characterized by an intensity of scientific activity rarely seen in astronomy. Observatories around the world adjusted their schedules, cancelling or postponing other observations to focus their instruments on this unprecedented visitor. The object, initially designated A2017U1 according to standard naming conventions for new discoveries, demanded immediate attention because every passing hour meant it was moving farther away, growing dimmer and becoming more difficult to study. The process of understanding what astronomers had found began with the fundamental task of precisely determining the object's orbit. While the initial observations had revealed the hyperbolic nature of its trajectory, confirming and refining these calculations required multiple observations from different locations over several days. Each telescope that captured the object's position added another data point, allowing astronomers to trace its path backward to where it had come from and forward to where it was going. The mathematical framework for understanding orbital motion dates back to Johannes Kepler and Isaac Newton, but applying these principles to an interstellar object presented unique challenges. For objects bound to our solar system, astronomers can often observe multiple orbits, refining their calculations over time. With this visitor, there would be only one chance. The margin for error was essentially zero, as any mistakes in the early calculations could lead to losing track of the object entirely as it faded from view. Dr. Karen Meach from the Institute for Astronomy at the University of Hawaii led much of the early observational campaign. Her team worked around the clock, coordinating observations from multiple telescopes and analysing the incoming data. The picture that emerged from these efforts was remarkable. The object had entered our solar system from above the plane of the planets, diving down toward the Sun at an angle of about 122 degrees from the ecliptic plane. The trajectory calculations revealed that the object had been travelling through interstellar space for millions, perhaps billions of years before its encounter with our solar system. It had approached from the direction of the constellation Lyra, moving at a velocity that suggested it wasn't gravitationally bound to any nearby star. This wasn't an object that had been recently ejected from a neighbouring star system. It was a true wanderer of the interstellar void. Understanding the object's velocity required careful consideration of different reference frames. When astronomers first detected it, the object was moving at about 26 kilometers per second relative to the Sun. But this measurement alone doesn't tell the complete story. To understand where the object came from, astronomers needed to calculate its velocity relative to the local standard of rest, essentially the average motion of stars in our neighbourhood of the galaxy. When calculated in this reference frame, the object's approach velocity was about 26 kilometers per second, remarkably close to the median velocity of stars in our local neighbourhood. This suggested that the object might have been floating in interstellar space for an extremely long time, long enough for its motion to have been randomized by gravitational interactions with many stars over millions or billions of years. The spectroscopic observations provided crucial information about the object's composition, or at least its surface properties. Different materials reflect and absorb light at different wavelengths, creating spectral signatures that can reveal their chemical composition. Teams using large telescopes like the Very Large Telescope in Chile and the Gemini telescopes in Hawaii and Chile obtained spectra of the object across visible and near-infrared wavelengths. What they found, or rather, what they didn't find, was puzzling. The spectra were remarkably featureless, showing a slightly reddish colour similar to some outer solar system objects, but lacking the distinct absorption features that would indicate specific minerals or ices. This reddish colour could result from cosmic ray irradiation over millions of years, creating complex organic compounds on the surface, a process known as space weathering. The absence of spectral features made it difficult to determine the object's composition definitively. It didn't show the signatures of water ice or other volatile compounds that might be expected on a comet. It also didn't display the clear mineralogical features typical of different types of asteroids. The surface appeared to be relatively uniform in composition, or at least in the properties that affect how it reflects light. One of the most striking discoveries came from photometric observations, measurements of how the object's brightness changed over time. These observations revealed dramatic variations in brightness as the object rotated, with the brightness changing by a factor of 10 over a period of about 7 to 8 hours. Such extreme brightness variations had never been observed in any solar system asteroid or comet. The interpretation of these brightness variations led to one of the most controversial aspects of the object's characterization: its shape. For the brightness to vary by such a large factor, the object needed to be highly elongated. Initial estimates suggested an axis ratio of about 6:1, meaning it was 6 times longer than it was wide. Later analyses pushed this ratio even higher, with some estimates suggesting the object could be 10 times longer than its width. This extreme elongation presented theoretical challenges. How could such an elongated object form naturally? In our solar system, asteroids and comets show a range of shapes, but nothing approaching this level of elongation. The most elongated asteroids known have axis ratios of about 3:1. The forces involved in planetary formation and subsequent collisions tend to produce more spheroidal or modestly elongated objects, not the extreme cigar or pancake shape suggested by the observations. The rotation itself was complex, not a simple spin around a single axis, but rather a tumbling motion that astronomers call non-principal axis rotation. This type of rotation is unstable over long timescales, suggesting that the object might have experienced a recent collision or gravitational interaction that set it tumbling. But if the object had been travelling through interstellar space for millions of years, what could have caused such recent disruption? Temperature measurements using infrared telescopes provided additional constraints on the object's properties. The Spitzer Space Telescope, NASA's infrared observatory, attempted to detect thermal emission from the object. The non-detection placed upper limits on its size, suggesting it was relatively small, perhaps a few hundred meters in length. This size estimate, combined with the brightness observations, helped constrain the object's reflectivity or albedo. The challenge of determining the object's size illustrates a fundamental problem in astronomy. When observing a distant point of light, astronomers can measure its apparent brightness, but determining its actual size requires knowing how reflective it is. A small, highly reflective object can appear as bright as a large dark object. Without resolved images showing the object's actual shape, astronomers had to make assumptions about its reflectivity to estimate its size. As data accumulated from observatories around the world, astronomers began to construct models to explain the object's properties. One class of models suggested it might be a fragment of a larger body, perhaps debris from a collision in another star system. Such collisions could potentially produce elongated fragments, though achieving the extreme axis ratio observed remained challenging to explain. Another possibility was that the object had been shaped by tidal forces during a close encounter with a star or planet in its original system. If the object had passed very close to a massive body, tidal forces could have stretched it into an elongated shape. However, such an encounter would likely have destroyed a loosely bound rubble pile, suggesting the object would need considerable internal strength to survive. The lack of cometary activity, despite the object's close approach to the Sun, provided important constraints on its composition. Most comets in our solar system begin showing activity, developing their characteristic comas and tails when they come within about 3 astronomical units of the Sun. This object had passed much closer without showing any signs of outgassing, suggesting either that it lacked volatile materials or that they were somehow sealed beneath an insulating crust. Some astronomers proposed that the object might be covered with an insulating mantle formed during its long journey through interstellar space. Cosmic rays could have processed the surface materials, creating a crust that prevented any remaining volatiles from sublimating even during the close solar approach. This explanation could reconcile the object's apparently inert nature with models suggesting that most interstellar objects should be icy bodies ejected from the outer regions of planetary systems. The discovery raised fundamental questions about the population of interstellar objects. If this was the first one detected, how many others had passed through our solar system unnoticed? Statistical arguments suggested that for pan-stars to have detected this object, there must be an enormous population of similar objects in interstellar space, perhaps one within every cubic astronomical unit on average. This implied that our solar system is regularly visited by interstellar objects, perhaps several per year, most passing through undetected because they're too faint or follow trajectories that keep them far from Earth. The discovery suggested that interstellar space might be filled with the debris of planetary formation, objects ejected from young star systems during the chaotic early stages of planet formation. The international nature of the observation campaign highlighted the collaborative spirit of modern astronomy. Data from telescopes in Hawaii, Chile, Arizona, the Canary Islands, and space-based observatories were freely shared among research groups. This cooperation was essential given the time-critical nature of the observations. As the object moved away from the Sun and Earth, it was fading at a rate of about 1 magnitude every month, meaning it was becoming 2.5 times fainter every 30 days. By early November, just 2 weeks after discovery, the object had already faded beyond the reach of all but the largest telescopes. The window for detailed observations was closing rapidly. Astronomers worked frantically to extract every possible piece of information from their observations, knowing that once the object faded from view, it would be gone forever, continuing its journey through interstellar space, where no human instrument could follow. The urgency of the situation led to some unprecedented decisions in telescope time allocation. The European Southern Observatory granted directors discretionary time for observations with the Very Large Telescope, bypassing the normal proposal process that can take months. The Hubble Space Telescope, usually scheduled many months in advance, was quickly retargeted to observe the object. These decisions reflected the scientific community's recognition that this was a unique opportunity that would not come again. As the observational window closed, astronomers were left with a dataset that was both rich and frustratingly incomplete. They had learned enough to know that this object was unlike anything in our solar system, but not enough to definitively determine its nature or origin. The data would be analysed and reanalyzed for years to come, with different research groups reaching different conclusions about the object's properties. The process of peer review began even as observations continued. Scientific papers were written, submitted to journals, reviewed by other experts, revised, and published at an unprecedented pace. The first paper announcing the discovery appeared in Nature just a month after the initial detection. This rapid publication reflected both the importance of the discovery and the astronomical community's desire to share information quickly while observations were still possible. The naming of celestial objects typically follows well-established conventions set by the International Astronomical Union, conventions that reflect centuries of astronomical tradition while accommodating the needs of modern science. But this object presented a unique challenge. It was neither asteroid nor comet in the traditional sense, and it certainly wasn't from our solar system. A new classification and naming scheme would be needed for this first confirmed interstellar visitor. Initially designated A2017U1, the object carried a name that was purely functional, indicating it was an asteroid-like object discovered in the first half of October 2017. But this clinical designation failed to capture the profound significance of the discovery. This wasn't just another space rock to be catalogued and forgotten. This was humanity's first confirmed visitor from another star system, an object that deserved a name reflecting its unique status. The International Astronomical Union moved quickly to establish a new naming convention for interstellar objects. They created a new designation system using the letter I for interstellar, making this object ʻOumuamua, the first interstellar object discovered in 2017. But while this formal designation served scientific purposes, there was recognition that such a historic discovery deserved a more meaningful name. The tradition in astronomy has long been to name objects after mythological figures, scientists, or in some cases, to honour the cultures and locations associated with their discovery. Given that this object was discovered using a telescope in Hawaii, and given the profound connection between Hawaiian culture and navigation, the Discovery team felt it appropriate to consult with Hawaiian language and culture experts to find a suitable name. The team reached out to Larry Kimura, a professor of Hawaiian language and Hawaiian studies at the University of Hawaii at Hilo, and his daughter, Ka'u Kimura, who serves as the executive director of the Imiloa Astronomy Center. Together, they considered various Hawaiian words and concepts that might capture the essence of this interstellar visitor. Hawaiian culture has a rich tradition of navigation and exploration. The Polynesian peoples who first settled Hawaii were master navigators who crossed thousands of miles of open ocean using their knowledge of stars, currents, and winds. They understood the night sky intimately, using it as both map and compass for their voyages across the Pacific. This cultural heritage made Hawaiian particularly appropriate for naming an object that had navigated across the far vaster ocean of interstellar space. After careful consideration, the Kaimura suggested the name ʻOumuamua, a word that carries deep meaning in Hawaiian. The name combines u, meaning to reach out or scout, and mua, which appears twice for emphasis and means first or in advance. Together, ʻOumuamua can be translated as scout from afar or first messenger from a distant place. The name resonated perfectly with both the scientific nature of the discovery and its deeper significance. Here was indeed a scout from afar, an advanced messenger from another star system reaching across the vast distances of interstellar space to briefly visit our cosmic neighborhood. The doubling of mua emphasized that this was the first such messenger we had detected, acknowledging both the historic nature of the discovery and the likelihood that other such objects would follow. The pronunciation of ʻOumuamua reflects the musical nature of the Hawaiian language. The initial character, the okina, represents a glottal stop, a brief pause in speech that is a consonant in Hawaiian. The name is pronounced roughly as ʻOumuamua, with emphasis on the first syllable of each mua. The flowing sound of the name seems to echo the object's smooth passage through our solar system. The choice of a Hawaiian name also honoured the crucial role that Hawaii plays in modern astronomy. The Hawaiian Islands host some of the world's most important observatories, taking advantage of the clear, stable air above the Pacific and the minimal light pollution. Mauna Kea, on the Big Island of Hawaii, hosts 13 telescopes operated by astronomers from 11 countries, making it one of the premier sites for astronomical observation on Earth. This relationship between Hawaii and astronomy has not been without controversy. The construction of telescopes on mountains that some native Hawaiians consider sacred has led to ongoing debates about the balance between scientific advancement and cultural preservation. The naming of ʻOumuamua represented a positive moment in this sometimes tense relationship, showing how Hawaiian culture and language could contribute to and be honoured by astronomical discovery. The name ʻOumuamua quickly captured public imagination in a way that 1i 2017 U1 never could have. Media outlets around the world attempted to pronounce and explain the name, often with varying degrees of success. The exotic sound of the name to non-Hawaiian speakers added to the object's mystique, reinforcing its status as something truly alien, a visitor from beyond our familiar cosmic shores. Beyond its literal meaning, the name ʻOumuamua carries metaphorical weight that extends into how we think about exploration and discovery. In Hawaiian navigation traditions, scouts would be sent ahead to find new lands, reporting back to guide those who would follow. ʻOumuamua could be seen as such a scout, not sent by anyone, but arriving nonetheless as a herald of what lies beyond our solar system. The naming process also highlighted the importance of language in how we conceptualize and relate to astronomical discoveries. A name is more than just a label. It shapes how we think about an object and its significance. By choosing a name that emphasized exploration and messaging rather than simply cataloguing another space rock, the astronomical community acknowledged that ʻOumuamua represented something fundamentally different from previous discoveries. The Hawaiian language itself embodies concepts that proved remarkably appropriate for this interstellar visitor. Hawaiian has words for various types of journeys and arrivals, distinguishing between different purposes and meanings of travel. The choice of ʻOumuamua, with its emphasis on scouting and reaching out, suggested agency and purpose, even if that purpose was simply the random wandering of a cosmic castaway. The cultural exchange involved in the naming process extended beyond just selecting a word. It required understanding the cultural context and significance of the name, ensuring that it was used respectfully and appropriately. The collaboration between astronomers and Hawaiian language experts demonstrated how modern science can honour and incorporate indigenous knowledge and perspectives. As news of the name spread, it sparked interest in Hawaiian language and culture around the world. Language learning websites reported increased searches for Hawaiian words and pronunciation guides. The Imiloa Astronomy Centre, which bridges Hawaiian culture and astronomy, saw increased interest in its programs. In this way, ʻOumuamua became not just a scientific discovery, but a cultural ambassador, introducing people worldwide to aspects of Hawaiian heritage. The name also influenced how scientists and science communicators discussed the object. Rather than referring to it by a sterile alphanumeric designation, they could speak of ʻOumuamua as almost a character in a cosmic story. This personification, subtle though it might be, helped make the discovery more relatable and engaging to the general public. The precedent set by naming this first interstellar object would influence how future such discoveries would be handled. When a second interstellar object was discovered in 2019, it was named Tuʻai Borisov after its discoverer, following the tradition for comets. But the impact of the name ʻOumuamua had already established that interstellar objects deserved names that acknowledged their special status. The linguistic aspects of the name revealed interesting patterns in how different languages and cultures adapted it. Some languages attempted direct translations of the Hawaiian meaning, while others transliterated the sound. Scientific papers in various languages had to decide whether to use the Hawaiian name with its okina or to adapt it to their own writing systems. These decisions reflected broader questions about how science, as an international enterprise, handles cultural and linguistic diversity. The name ʻOumuamua also entered popular culture remarkably quickly. It appeared in science fiction stories, music and art. Its exotic sound and profound meaning made it a natural fit for creative works, exploring themes of cosmic loneliness, first contact, and the vastness of the universe. The name became shorthand for the mysterious and unknown, for visitors from beyond our understanding. Educational materials about ʻOumuamua often included lessons about Hawaiian culture and language, creating unexpected connections between astronomy and cultural studies. Students learning about this interstellar visitor also learned about the Polynesian navigators who crossed the Pacific, drawing parallels between different scales and eras of exploration. The process of naming ʻOumuamua also raised questions about how we will name future interstellar visitors. Should they all receive names from Hawaiian or other Polynesian languages, honouring the navigation traditions of these cultures? Should names rotate among different Earth cultures? Or should each discovery team choose based on their own circumstances and preferences? These questions remain open as we await the next interstellar visitor. The name has proven remarkably durable and memorable. Years after the discovery, ʻOumuamua remains a household name among those interested in astronomy, far more recognizable than most asteroids or comets discovered around the same time. This staying power demonstrates the importance of thoughtful naming in making scientific discoveries accessible and memorable to the public. The physical nature of Oumuamua remains one of the most debated and mysterious aspects of this interstellar visitor. Unlike the planets, asteroids and comets we can study in detail, within our solar system, Oumuamua presented astronomers with only a brief window of observation, during which it appeared as nothing more than a point of light in even our most powerful telescopes. From this limited data, scientists have had to piece together a picture of what this object actually looked like, leading to interpretations that range from the conservative to the extraordinary. The most striking characteristic of Oumuamua, and the one that generated the most discussion and controversy, was its apparent shape. The dramatic variations in brightness as the object rotated indicated that it was far more elongated than any natural object previously observed in our solar system. As Oumuamua tumbled through space, its brightness varied by a factor of 10 over its rotation period of approximately 7 to 8 hours. This extreme variation suggested an object that was presenting vastly different cross-sectional areas to observers as it rotated. Initial models suggested that Oumuamua was shaped something like a cigar, perhaps 400 meters long and 40 meters wide, giving it an axis ratio of about 10 to 1. This would make it roughly the size of a skyscraper laid on its side, tumbling end over end through space. Such an elongated shape immediately raised questions about how such an object could form and survive. In our solar system, the most elongated asteroids have axis ratios of about 3 to 1, and even these are considered unusual. However, the cigar shape was not the only possibility. Some astronomers proposed that Oumuamua might instead be shaped like a pancake, a flattened disk that would also produce large brightness variations as it tumbled. This interpretation suggested an object perhaps 115 meters across but only 20 meters thick, resembling a cosmic frisbee spinning through space. The pancake model had certain advantages in explaining some of the observed characteristics, but it too presented challenges in terms of formation and stability. The debate over Oumuamua's shape highlighted a fundamental challenge in astronomy: determining three-dimensional shapes from one-dimensional brightness measurements. Without resolved images showing the actual outline of the object, astronomers had to rely on models of how different shapes would reflect sunlight as they rotated. These models depended on assumptions about the object's surface properties, its rotation state, and the distribution of material within it. The rotation itself was complex and unusual. Oumuamua was not simply spinning around a single axis like a well-thrown football. Instead, it was tumbling in what astronomers call a non-principal axis rotation state, more like a poorly thrown pass that wobbles through the air. This type of rotation is unstable over astronomical timescales, meaning that internal friction should cause it to decay into simple rotation around the axis of maximum inertia within a few 100 million years. The fact that Oumuamua was observed in this excited rotation state suggested several possibilities. Perhaps it had experienced a recent collision or close gravitational encounter that set it tumbling, or perhaps the outgassing that would later be proposed to explain its acceleration had created torques that excited the rotation. Some researchers even suggested that the tumbling might indicate that Oumuamua was not a solid body, but rather a fractal aggregate of dust and ice, though this interpretation faced its own challenges. The surface properties of Oumuamua provided another set of clues about its nature. Spectroscopic observations revealed that the object had a slightly reddish colour, similar to some outer solar system objects, like Kuiper belt objects or D-type asteroids. This red colour is typically attributed to the presence of complex organic compounds called tholins, created when simple molecules are exposed to cosmic radiation over long periods. The reddish colour suggested that Oumuamua's surface had been processed by its long exposure to cosmic rays during its interstellar journey. This space weathering would have altered the original surface composition, creating a crust of irradiated material. Some scientists proposed that this crust might be insulating a more volatile, rich interior, explaining why the object showed no obvious cometary activity despite its close approach to the Sun. The reflectivity, or albedo, of Oumuamua was another important but uncertain parameter. Different assumptions about its reflectivity led to different estimates of its size. If the object was highly reflective, like a fresh icy surface, it could be smaller than if it had a dark surface like many carbonaceous asteroids. Most models assumed a moderate albedo similar to typical asteroids, but this assumption significantly affected the derived physical dimensions. Temperature considerations added another layer to understanding Oumuamua's physical state. During its closest approach to the Sun, the object would have been heated to temperatures exceeding 400 degrees Celsius on its sunlit side. This heating should have been sufficient to sublimate water ice and other volatile compounds if they were present at or near the surface. The lack of observed outgassing during this period suggested either that the object lacked such volatiles or that they were somehow protected from the solar heating. The thermal properties of Oumuamua also influenced its rotation. As the object absorbed sunlight and re-radiated heat, the delayed thermal emission could create small torques that would gradually change its rotation state. This Yarkovsky-O'Keefe-Radzievsky-Paddock effect, known as the Yorp effect, has been observed in solar system asteroids and could potentially explain some aspects of Oumuamua's complex rotation. One of the most intriguing proposals about Oumuamua's physical nature came from researchers who suggested it might be composed of molecular hydrogen ice. This exotic composition would make Oumuamua unlike anything in our solar system, where temperatures are too high for hydrogen to freeze. In the cold depths of interstellar space, however, hydrogen ice might form in dense molecular clouds. Such an object would be essentially invisible to spectroscopic observations, as hydrogen ice lacks strong spectral features, potentially explaining the featureless spectra observed. The hydrogen ice hypothesis had several attractive features. It could explain the lack of visible outgassing, as hydrogen gas would be difficult to detect. It could also naturally explain the acceleration that would later be observed, as hydrogen sublimates at very low temperatures and could provide thrust even far from the Sun. However, this model faced challenges too, particularly in explaining how a hydrogen ice object could survive its journey through interstellar space without completely evaporating. Another exotic possibility was that Oumuamua might be a dust bunny, a very low-density aggregate of dust particles held together by weak van der Waals forces. Such structures can form in protoplanetary disks and might be ejected into interstellar space. A dust bunny structure could potentially explain both the elongated shape and the unusual acceleration, as solar radiation pressure would have a stronger effect on such a low-density object. However, critics argued that such a fragile structure would likely be destroyed by its tumbling rotation. The strength and internal structure of Oumuamua became subjects of intense theoretical investigation. For the object to maintain its elongated shape while tumbling, it needed sufficient tensile strength to resist being torn apart by centrifugal forces. Calculations suggested that if Oumuamua was indeed as elongated as the light curve suggested, it needed to have the cohesive strength of at least a rubble pile asteroid held together by gravity and possibly some internal strength. Some researchers propose that Oumuamua might be a fragment of a larger body that was disrupted by tidal forces during a close encounter with its host star. Such tidal disruption could potentially create elongated fragments, and computer simulations showed that under certain conditions, very elongated shapes could be produced. These fragments would need to be relatively strong, monolithic pieces rather than loose rubble piles to survive both the initial disruption and the subsequent journey through interstellar space. The possibility that Oumuamua might be a contact binary, two separate bodies held together by gravity, was also considered. Some solar system comets and asteroids are known to have this dumbbell-like structure, which could produce large brightness variations. However, the smooth nature of the observed light curve argued against this interpretation, as a contact binary would typically produce more irregular brightness variations. Size estimates for Oumuamua varied depending on the assumptions made about its shape and reflectivity. If it was cigar-shaped with moderate reflectivity, it might be about 400 meters long. If it was pancake-shaped, it might be only about 100 meters across but very thin. These size estimates placed it in the range of small asteroids or large meteoroids, objects that are common in our solar system, but usually too small to detect at interstellar distances. The surface texture of Oumuamua remained entirely unknown, as no telescope could resolve surface features. It might have been smooth like a polished stone, rough and cratered like most asteroids, or something entirely different. Some models suggested that erosion by interstellar dust grains over millions of years might have smoothed the surface, while others proposed that the surface might be extremely rough and fractal in nature. Colour variations across Oumuamua's surface, if they existed, were too subtle to detect with the available observations. The object appeared uniformly reddish, suggesting either a homogeneous surface composition or that any variations were smaller than could be measured. This apparent uniformity was somewhat surprising, as many solar system asteroids and comets show distinct colour variations across their surfaces. The internal structure of Oumuamua sparked considerable speculation. Was it a solid monolith, a rubble pile of loosely bound fragments, or something more exotic? Each possibility had different implications for the object's origin and evolution. A monolithic structure would suggest formation as a single piece, perhaps condensed from a protoplanetary disk or carved from a larger body. A rubble pile structure would indicate a collisional origin, assembled from fragments of destroyed objects. Some of the most creative proposals for Oumuamua's structure came from considering processes that don't occur in our solar system but might be possible elsewhere. For instance, if Oumuamua formed in a protoplanetary disk much closer to its star than where asteroids form in our solar system, it might have experienced unique conditions that produced its unusual characteristics. Or, if it spent millions of years in the interstellar medium, it might have been altered by processes we don't fully understand. The possibility that Oumuamua might be porous or have significant internal voids was another area of investigation. A porous structure could affect how the object responded to heating, how it reflected light, and how it would accelerate under various forces. Some models suggested that Oumuamua might be more like a cosmic pumice stone than a solid rock, with a network of voids throughout its structure. Attempts to detect Oumuamua in radio wavelengths added another dimension to understanding its physical properties. The Breakthrough Listen project used the Green Bank telescope to search for radio emissions from Oumuamua, both to check for any signs of artificial technology and to potentially detect natural emissions that might reveal something about its composition or structure. No signals were detected, but the observations placed constraints on certain scenarios for the object's nature. The question of whether ʻOumuamua might be covered in an organic-rich crust became particularly interesting when considering its colour and spectral properties. Laboratory experiments showed that when simple ices containing carbon, hydrogen, oxygen, and nitrogen are exposed to radiation, they form complex reddish organic compounds. If ʻOumuamua had a similar crust, formed during millions of years of cosmic ray exposure, it might explain both its colour and its apparent lack of activity. As ʻOumuamua faded from view, astronomers were left with a collection of observations that painted a picture of an object unlike anything in our solar system. Its extreme elongation, complex rotation, unusual acceleration, and featureless spectrum all pointed to something genuinely alien. Not in the sense of artificial origin, but in the sense of being fundamentally different from the asteroids and comets we know. The path that ʻOumuamua traced through our solar system tells a story of cosmic coincidence and near misses, a tale written in the language of celestial mechanics and preserved in the precise measurements of its trajectory. This interstellar visitor's journey through our cosmic neighbourhood lasted only a few months from our perspective, but those months provided humanity with its first opportunity to study an object from another star system, and the details of its passage revealed as much about the nature of interstellar space as they did about the object itself. ʻOumuamua approached our solar system from above the ecliptic plane, the imaginary disk in which most planets orbit the Sun. It came from the direction of the constellation Lyra, home to the bright star Vega, though its velocity indicated it was not actually associated with that or any other specific star. Instead, it appeared to be a free-floating object, unbound to any star, wandering through the galaxy for millions or perhaps billions of years before its encounter with our Sun. The approach velocity of ʻOumuamua relative to the Sun was approximately 26 kilometers per second at infinity, meaning that was its speed far from the Sun's gravitational influence. This velocity is remarkably close to the local standard of rest, the average velocity of nearby stars relative to the Sun. This coincidence suggested that ʻOumuamua had been floating in interstellar space for so long that its motion had been randomized by encounters with many star systems, losing any memory of its original velocity from its parent system. As ʻOumuamua fell toward the Sun, it accelerated under the influence of solar gravity, following a hyperbolic trajectory that would take it in and then back out of the solar system. The mathematics of hyperbolic orbits had been understood since the time of Newton, but this was the first time astronomers had observed a macroscopic object from outside the solar system following such a path. Every previous comet and asteroid had followed either a closed elliptical orbit or, in rare cases, a barely hyperbolic orbit resulting from gravitational perturbations within the solar system. The closest approach to the Sun, called perihelion, occurred on September 9th, 2017, about 40 days before the object was discovered. At perihelion, ʻOumuamua passed within approximately 37 million kilometers of the Sun, or about 0.25 astronomical units. This placed it well inside Mercury's orbit, exposing it to intense solar radiation and heating. The sunlit side of the object would have reached temperatures exceeding 400 degrees Celsius, hot enough to melt lead, and certainly hot enough to sublimate any exposed water ice or other volatile compounds. The timing of perihelion before discovery meant that astronomers missed the opportunity to observe ʻOumuamua during its closest approach to the Sun, when any cometary activity would have been most pronounced. By the time the object was discovered in October, it had already passed perihelion and was heading back out toward interstellar space, cooling as it receded from the Sun. This unfortunate timing limited what could be learned about the object's composition and behavior under intense solar heating. After perihelion, Oumuamua's path took it relatively close to Earth, though never dangerously so. On October 14, 2017, 5 days before its discovery, the object passed within about 24 million kilometers of Earth, or about 60 times the distance to the Moon. This was the closest it would come to our planet, and even then, it was far too distant to see with the naked eye or even small telescopes. Only large professional instruments could detect this faint visitor. The trajectory of Oumuamua through the inner solar system was inclined at a steep angle to the ecliptic plane, about 122 degrees. This meant it was moving in almost the opposite direction to the planets, diving down from above the plane, passing close to the Sun, and then climbing back up and away. This unusual trajectory was one of the first clues that the object was not from our solar system, as most solar system objects orbit much closer to the ecliptic plane. As Oumuamua travelled through the solar system, it passed through the orbits of all the planets, though not necessarily close to the planets themselves. The vastness of space meant that despite crossing these orbital paths, Oumuamua never came particularly close to any planet other than Earth. Its closest approach to any of the giant planets was to Jupiter, but even that was at a distance of more than 2 astronomical units, too far for Jupiter's gravity to significantly affect its trajectory. The velocity of Oumuamua changed dramatically during its passage through the inner solar system. At perihelion, under the full influence of the Sun's gravity, it reached a maximum velocity of about 87 kilometers per second relative to the Sun. This is faster than any spacecraft humans have ever launched, and faster than the orbital velocity of any planet. As it climbed back out of the Sun's gravitational well, it decelerated, but because it was on a hyperbolic trajectory, it would never slow to zero velocity. Instead, it would leave the solar system with excess velocity, continuing its interstellar journey. One of the most intriguing aspects of Oumuamua's journey was the discovery of a small but measurable non-gravitational acceleration. As astronomers continued to track the object and refine its orbit, they found that it was deviating slightly from the path predicted by gravity alone. The object was accelerating away from the Sun slightly faster than it should have been, as if being pushed by some additional force. This anomalous acceleration was tiny, only about 1/1000th of a millimeter per second squared, but it was statistically significant and demanded explanation. In comets, such non-gravitational accelerations are common and well understood. They result from the rocket effect of outgassing as ices sublimate. But Oumuamua showed no visible signs of outgassing, no coma or tail that would indicate cometary activity. This paradox would become one of the central mysteries surrounding the object. The trajectory of Oumuamua was determined with remarkable precision through a combination of observations from multiple telescopes around the world. Each observation provided a position measurement, a point in space and time where the object was located. By combining dozens of such measurements over several weeks, astronomers could reconstruct the object's path with high accuracy, both backward in time to before its discovery and forward to predict where it would go. The process of orbit determination for Oumuamua required sophisticated mathematical techniques and powerful computers. Unlike solar system objects that can be observed over multiple orbits, allowing for iterative refinement of orbital parameters, Oumuamua offered only one chance. Every observation was precious, and the rapid fading of the object as it receded meant that the window for accurate position measurements was limited to just a few weeks. As Oumuamua continued its outward journey, it passed through the asteroid belt between Mars and Jupiter without any known close encounters with asteroids. The probability of collision with an asteroid was essentially zero, given the vast spaces between objects, even in the relatively crowded asteroid belt. The object continued to climb above the ecliptic plane, moving into regions of the solar system rarely visited by comets or asteroids. By December 2017, Oumuamua had passed beyond the orbit of Mars and was continuing to fade from view. The largest telescopes on Earth could still detect it, but it was becoming increasingly difficult to observe. The object was not only moving farther away, but also moving into parts of the sky that were difficult to observe from Earth's position in its orbit around the Sun. The European Space Agency's Gaia spacecraft, designed to map the positions of stars with unprecedented precision, attempted to observe Oumuamua but found it too faint. The Spitzer Space Telescope, observing in infrared wavelengths, also failed to detect the object, placing upper limits on its size and thermal emission. These non-detections were valuable in their own right, constraining models of the object's properties. By early 2018, Oumuamua had faded beyond the reach of even the most powerful telescopes. The last successful observations were made in January 2018 using the Hubble Space Telescope, which could still detect the object as a faint point of light against the background stars. After that, Oumuamua disappeared into the darkness, continuing its journey but now invisible to human instruments. The future trajectory of Oumuamua could be calculated with reasonable accuracy for thousands of years into the future, assuming no close encounters with other stars. The object would continue to slow gradually as it climbed out of the Sun's gravitational influence, eventually reaching a cruising speed of about 26 kilometers per second relative to the Sun. At this speed, it would take about 11,000 years to travel 1 light year. In about 10,000 years, Oumuamua will pass through the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. In about 20,000 years, it will reach the inner edge of the Oort cloud, the spherical cloud of comets that surrounds our solar system. It will take several 100,000 years to completely leave the Sun's gravitational influence and return to true interstellar space. The trajectory of Oumuamua raised interesting questions about where it came from and where it was going. Tracing its path backward, astronomers found that it came from the general direction of the solar apex, the direction the Sun is moving through space. This was not particularly surprising, as objects at rest relative to the local standard of rest would appear to come from this direction. But it meant that identifying a specific star system as Oumuamua's origin was essentially impossible. Statistical analyses suggested that Oumuamua had probably been wandering through interstellar space for millions or even billions of years. During this time, it would have passed through or near many star systems, each encounter slightly altering its trajectory. These gravitational perturbations would have randomized its orbit, erasing any information about its original home. Looking forward, Oumuamua's future encounters with other star systems could be predicted, at least for the next few million years. The object will pass within a few light years of several stars over the coming millennia, though none of these encounters will be close enough to significantly alter its trajectory. It will continue its lonely journey through the galaxy, a perpetual wanderer between the stars. The scientific community's attempts to explain the nature of Oumuamua produced a remarkable diversity of theories, each trying to account for the object's unusual combination of characteristics. These theories ranged from relatively mundane explanations involving familiar astrophysical processes to exotic proposals that push the boundaries of our understanding of planetary science, and even raised questions about the possibility of artificial origins. The debate over Oumuamua's nature became one of the most vibrant and contentious in recent astronomical history. The most conservative interpretation was that Oumuamua was simply an asteroid, a rocky or metallic body similar to the millions of asteroids in our own solar system, but ejected from another star system during planet formation. This theory had the advantage of simplicity and precedent. We know that gravitational interactions during planet formation can eject small bodies into interstellar space, and models of planetary system formation suggest that each system might eject quadrillions of such objects during its early chaotic phases. However, the asteroid hypothesis faced several challenges. The extreme elongation of Oumuamua was unlike any asteroid observed in our solar system. While some asteroids are elongated, none approach the 10-to-1 axis ratio suggested by Oumuamua's light curve. Additionally, the non-gravitational acceleration observed in Oumuamua's trajectory was difficult to explain for a purely rocky body without visible outgassing. The comet hypothesis seemed more promising in some ways. Comets are known to experience non-gravitational accelerations due to the rocket effect of sublimating ices, which could explain Oumuamua's trajectory anomaly. Models of planetary system formation suggest that most objects ejected into interstellar space should come from the outer regions of their systems, where ices are abundant, making an icy composition plausible. Yet the comet theory had its own problems. Despite passing close to the Sun, where heating should have activated any near-surface ices, Oumuamua showed no visible coma or tail, the hallmarks of cometary activity. Deep imaging observations that could detect extremely faint dust features found nothing. If Oumuamua was a comet, it was unlike any comet we had previously observed. To reconcile these contradictions, some scientists proposed that Oumuamua might be a comet with an unusual structure or composition. Perhaps it had developed a thick insulating crust during its long journey through interstellar space, preventing visible outgassing even when heated. Cosmic ray bombardment over millions of years could have created a layer of processed organic material, sealing in any remaining volatiles. When heated, gases might escape through small vents or pores without carrying enough dust to create a visible coma. The molecular hydrogen ice theory, proposed by researchers at Yale and the University of Chicago, offered a radically different explanation. They suggested that Oumuamua might be composed primarily of hydrogen ice, formed in the dense cores of molecular clouds where temperatures approach absolute zero. Hydrogen ice would sublimate at very low temperatures, providing thrust even far from the Sun, and hydrogen gas would be nearly impossible to detect with the observations that were made. This theory could elegantly explain both the non-gravitational acceleration and the lack of visible outgassing. It also provided a natural formation mechanism, as hydrogen ice objects might form in the coldest regions of space, and occasionally be scattered into planetary systems. However, critics argued that hydrogen ice would be too fragile to survive the journey through interstellar space, where heating from cosmic rays and starlight would cause it to evaporate over millions of years. Another exotic proposal was the nitrogen ice fragment hypothesis, suggested by researchers at Arizona State University. They proposed that Oumuamua might be a chunk of nitrogen ice, similar to the surfaces of Pluto and Neptune's moon Triton, broken off from an exopluto in another star system. Nitrogen ice would sublimate without producing much visible dust, potentially explaining the lack of a coma, and could provide the observed acceleration. The nitrogen ice theory had the advantage of invoking materials we know exist in our own outer solar system. If other star systems have Kuiper belts with Pluto-like objects, collisions could produce fragments that get ejected into interstellar space. The theory could also explain Oumuamua's albedo and colour, which were consistent with processed nitrogen ice surfaces observed in our solar system. The dust bunny, or fractal aggregate theory, proposed that Oumuamua might be an extremely low-density collection of dust particles held together by weak forces. Such structures might form in protoplanetary disks and could be ejected during planet formation. Their low density would make them highly susceptible to radiation pressure, potentially explaining the non-gravitational acceleration without requiring outgassing. This theory faced challenges in explaining how such a fragile structure could survive its tumbling rotation and interstellar journey. Critics calculated that the centrifugal forces from Oumuamua's rotation would tear apart a dust aggregate unless it had more structural integrity than such models typically predict. Additionally, the formation and ejection of such large, low-density aggregates had not been demonstrated in planet formation models. Some researchers proposed that ʻOumuamua might be a fragment from a tidally disrupted body. If a planet or large asteroid passed too close to its star, tidal forces could tear it apart, potentially creating elongated fragments. Computer simulations showed that under certain conditions, very elongated shapes could be produced by tidal disruption, and the fragments would be launched into interstellar space with high velocity. The tidal disruption theory could explain Oumuamua's unusual shape and its apparent strength, as the fragment would need to be a coherent piece of rock rather than a rubble pile to survive. However, the theory required fairly specific conditions for the disruption event and didn't naturally explain the non-gravitational acceleration unless combined with some form of outgassing. Perhaps the most controversial theory was the suggestion that ʻOumuamua might be artificial in origin. Avi Loeb, chair of Harvard's astronomy department, proposed that ʻOumuamua could be a piece of alien technology, possibly a light sail or probe sent by an extraterrestrial civilization. This hypothesis was based primarily on the object's unusual acceleration, which Loeb argued was consistent with the effect of solar radiation pressure on a thin, low-density object. The artificial origin hypothesis generated enormous media attention and significant scientific pushback. Critics argued that natural explanations had not been exhausted and that invoking aliens was premature. They pointed out that the acceleration could be explained by various natural mechanisms and that nothing about ʻOumuamua required an artificial origin. The debate highlighted tensions in how scientists approach anomalous observations and the role of speculation in scientific discourse. Statistical arguments played a crucial role in theorizing about Oumuamua's nature. If it was a typical interstellar object, its detection implied an enormous population of such objects, perhaps one per cubic astronomical unit throughout the galaxy. This abundance seemed too high if interstellar objects were primarily rocky asteroids, but might be reasonable if many were icy bodies from the outer regions of planetary systems. The discovery prompted theoretical work on the expected properties of interstellar objects. Models of planet formation and dynamics were used to predict what types of objects should be ejected, their size distribution, and their likely compositions. These models generally predicted that most interstellar objects should be icy rather than rocky, and smaller rather than larger, though the uncertainties were substantial. Laboratory experiments attempted to recreate conditions that might explain Oumuamua's properties. Scientists created and studied various types of ices under conditions simulating interstellar space, looking for materials that might sublimate without producing visible dust. They investigated how cosmic ray bombardment might alter surface compositions and create insulating crusts. These experiments provided constraints on possible compositions, but couldn't definitively identify what Oumuamua was made of. The role of selection effects in our detection of Oumuamua became an important consideration. We detected this object because it passed relatively close to Earth and Sun, was large enough to be visible, and happened to be discovered by our surveys. These selection effects meant that Oumuamua might not be representative of typical interstellar objects. Perhaps we preferentially detect unusual objects because normal ones are too faint or pass too far away. Comparative planetology offered another perspective on Oumuamua's nature by studying the diversity of objects in our own solar system, from metallic asteroids to icy comets to the exotic surfaces of outer solar system moons. Scientists could constrain the range of possible compositions for Oumuamua. The discovery of increasingly unusual objects in our own Kuiper belt suggested that the diversity of planetary building blocks might be greater than previously thought. The discovery that Oumuamua was accelerating in a way that couldn't be explained by gravity alone became the central mystery that would define scientific and public discourse about this interstellar visitor. This non-gravitational acceleration was subtle, measuring only about 1/1000th of a millimetre per second squared, but it was statistically significant and demanded explanation. The effort to understand this acceleration would push astronomers to consider increasingly exotic possibilities and ultimately leave the mystery unresolved. The first hints of anomalous motion came as astronomers continued to track Oumuamua in the weeks following its discovery. Marco Micheli from the European Space Agency and his colleagues were working to refine the object's trajectory using observations from telescopes around the world and the Hubble Space Telescope. Their goal was to determine Oumuamua's path with sufficient precision to trace back where it came from and predict where it was going. As they added more observations to their orbital solution, a systematic pattern emerged in the residuals. The differences between where Oumuamua was observed and where it should have been based on a purely gravitational trajectory. The object was consistently appearing slightly ahead of its predicted position, as if something was giving it an extra push away from the Sun. At first, the team suspected measurement errors or uncertainties in the data reduction, but as more observations accumulated, the signal became undeniable. The magnitude of the acceleration was tiny by everyday standards, but significant in the context of celestial mechanics. The extra push was causing Oumuamua to deviate from its expected path by about 40,000 kilometers by early 2018, just a few months after discovery. While this might seem like a small deviation, given the vast scales of the solar system, it was far larger than could be explained by measurement uncertainties or known gravitational perturbations. In our solar system, non-gravitational accelerations are commonly observed in comets. As a comet approaches the Sun, solar heating causes ices to sublimate, creating jets of gas that act like tiny rocket engines. This outgassing can significantly alter a comet's trajectory, sometimes making their paths difficult to predict. The magnitude of Oumuamua's acceleration was consistent with what might be expected from a comet of similar size, experiencing modest outgassing. However, Oumuamua showed none of the visible signs of cometary activity. Deep imaging observations found no evidence of a coma, the cloud of gas and dust that surrounds active comets. No tail was detected, even in stacked images that could reveal extremely faint features. Spectroscopic observations found no emission lines from gases like cyanogen or carbon that are typically seen in comets. If Oumuamua was outgassing, it was doing so in a way unlike any comet previously observed. The team led by Micheli explored various possibilities for the acceleration. They considered whether errors in the solar system's gravitational model might be responsible, but the effect was too large to be explained by uncertainties in planetary masses or positions. They investigated whether the Yarkovsky effect, the tiny push from asymmetric thermal emission, might be responsible, but calculations showed this effect would be far too small for an object of ʻOumuamua's likely size. The most natural explanation seemed to be cometary outgassing, but this required explaining why no coma was visible. One possibility was that ʻOumuamua was releasing primarily gas with very little dust. Some solar system comets, known as dark comets, show weak dust production, though none are completely dust-free. If ʻOumuamua's ice-to-dust ratio was extremely high, perhaps the dust coma was simply too faint to detect. Another possibility was that the outgassing was occurring through a small number of discrete vents rather than across the entire sunlit surface. Concentrated jets might produce thrust without creating a detectable coma, especially if the gas was something like hydrogen or helium that would be difficult to observe. This model required fairly specific assumptions about the object's structure and composition, but wasn't physically impossible. The discovery of the acceleration reignited debates about ʻOumuamua's composition. If it was outgassing, what volatile species could sublimate at the relatively large distances from the Sun where the acceleration was observed? Water ice, the most common volatile in solar system comets, typically becomes active within about 3 astronomical units of the Sun. But ʻOumuamua's acceleration was detected at distances where water ice sublimation should be negligible. This led to proposals involving more volatile species. Carbon monoxide ice sublimates at much lower temperatures than water and could potentially be active at the distances where ʻOumuamua showed acceleration. Nitrogen ice, as suggested in the exo-Pluto fragment theory, was another possibility. These super-volatile ices could provide thrust without producing much visible dust, potentially explaining the observations. The molecular hydrogen ice theory gained traction as an explanation for the acceleration. Hydrogen ice would sublimate at extremely low temperatures, providing thrust even far from the Sun. Hydrogen gas would be nearly impossible to detect with the observations that were made of ʻOumuamua, explaining the lack of visible outgassing. The theory predicted an acceleration magnitude consistent with observations if ʻOumuamua was a hydrogen ice object of the right size. However, the hydrogen ice theory faced serious challenges. Critics calculated that a hydrogen ice object would evaporate quickly when exposed to starlight during its interstellar journey. Even in the cold of interstellar space, the heating from distant stars and the cosmic microwave background would cause hydrogen ice to sublimate. Unless ʻOumuamua had been travelling for a much shorter time than seemed likely, or had some mechanism to protect the hydrogen ice, this theory seemed problematic. The acceleration mystery became central to arguments about ʻOumuamua's possible artificial origin. Avi Loeb and his collaborator Shmuel Bialy calculated that the observed acceleration could be explained by solar radiation pressure if ʻOumuamua was a thin sheet with a mass-to-area ratio of about 1 gram per square metre. This was consistent with a light sail, a propulsion technology that humans have considered for interstellar travel. The light sail hypothesis was controversial for several reasons. First, it required ʻOumuamua to be extraordinarily thin, perhaps less than a millimetre thick despite being hundreds of metres across. Such a structure seemed unlikely to survive interstellar travel and the tumbling rotation observed. Second, the hypothesis required abandoning natural explanations before they had been fully explored, violating the scientific principle of parsimony. Critics of the artificial origin hypothesis pointed out that the acceleration was not constant but varied with distance from the Sun in a way consistent with temperature-dependent outgassing. A light sail would experience a force proportional to the inverse square of distance from the Sun, while outgassing would follow a more complex relationship depending on temperature. The observed acceleration pattern seemed more consistent with outgassing, though the uncertainties were large. The debate over the acceleration mechanism highlighted deeper issues in how science deals with anomalous observations. Some scientists argued for sticking with conventional explanations, even if they required special pleading about invisible outgassing or exotic ices. Others argued that the failure of conventional explanations justified considering more radical possibilities, including artificial origins. The controversy played out in scientific journals, conferences, and the media. Alternative mechanisms for the acceleration were proposed and debated. Some researchers suggested that electromagnetic forces might play a role if Oumuamua had become electrically charged during its interstellar journey. Others proposed that the object might be experiencing drag from the solar wind or interplanetary medium, though calculations showed these effects would be far too small. The possibility that the acceleration was not real but rather an artifact of measurement or analysis was thoroughly investigated. Independent teams reanalyzed the astrometric data, confirming the basic result. The acceleration signal was robust to different choices of data, weighting, orbital fitting methods, and observation selection. While the exact magnitude remained uncertain, the existence of non-gravitational acceleration was well established. As Oumuamua faded from view, the acceleration mystery remained unresolved. The object's trajectory had been measured with sufficient precision to confirm that something besides gravity was affecting its motion, but the cause of this acceleration couldn't be definitively determined. Each proposed explanation had strengths and weaknesses, and the limited observational data couldn't distinguish between them. The question of where Oumuamua came from captivated scientists and the public alike, representing one of the most profound mysteries surrounding this interstellar visitor. Unlike comets and asteroids in our solar system, whose orbits can be traced back to specific regions or even parent bodies, Oumuamua's origin was shrouded in the vastness of interstellar space and the deep time of its journey between the stars. The search for its home would reveal as much about the nature of planetary systems and stellar dynamics as it would about this specific object. When astronomers first calculated Oumuamua's trajectory, they found it had entered our solar system from the direction of the constellation Lyra, not far from the bright star Vega. This immediately sparked speculation that Vega might be Oumuamua's home star, but further analysis quickly ruled out this possibility. Vega is about 25 light-years from Earth, and even at Oumuamua's considerable velocity, it would have taken about 600,000 years to travel from Vega to our solar system. However, Vega itself has moved significantly through space during that time, and was nowhere near its current position 600,000 years ago. This highlighted a fundamental challenge in tracing Oumuamua's origin. Stars are not fixed in space, but orbit around the galaxy, each following its own path through the cosmic dance of gravitational interactions. Over the millions or billions of years that Oumuamua had likely been travelling, every star in our galactic neighbourhood had completed multiple orbits around the galactic centre, their position shifting dramatically. The task of finding Oumuamua's home was like trying to identify which tree in a wind-blown forest had dropped a particular leaf after the forest itself had migrated across continents. The velocity of Oumuamua provided crucial clues about its history. The object approached our solar system at about 26 kilometers per second relative to the Sun, but more revealing was its velocity relative to the local standard of rest, the average motion of stars in our neighbourhood. In this reference frame, Oumuamua was moving remarkably slowly, suggesting it had been drifting through interstellar space for an extremely long time, its original velocity erased by countless distant gravitational encounters. Astronomers attempted to trace Oumuamua's path backward through time, accounting for the gravitational influences of nearby stars. This required sophisticated computer simulations that modelled the motions of thousands of stars over millions of years. The calculations were inherently uncertain, as small errors in stellar positions and velocities compound over time, and many stars that might have influenced Oumuamua's trajectory in the past are too faint to have been catalogued. The European Space Agency's Gaia mission, which has measured precise positions and velocities for over 1 billion stars, provided the most comprehensive dataset for this stellar archaeology. Researchers used Gaia data to identify stars that Oumuamua might have encountered in the past few million years. They found several possible candidates, stars whose paths had brought them close enough to Oumuamua's trajectory that they might have been its source. One intriguing candidate was the star HD 2003-25, which came within about 3 light-years of Oumuamua's path about 1 million years ago. Another possibility was the binary star system Carina Near Moving Group, which had a similar close approach. However, these encounters were not particularly close by stellar standards, and the uncertainties in the calculations meant that hundreds of other stars were equally plausible candidates. The search expanded to consider not just individual stars, but also stellar associations and moving groups, collections of stars that form together and share similar motions through space. If Oumuamua originated from a young star system, it might be possible to link it to one of these stellar families. The Pleiades Moving Group, the Tucana Horologium Association, and other young stellar groups were investigated, but no definitive connection could be established. The age of Oumuamua became a critical question in understanding its origin. If the object was relatively young, perhaps only millions of years old, it might be possible to trace it back to its parent star. But if it was billions of years old, as seemed more likely given its velocity characteristics, then its origin was lost in the complex gravitational choreography of the galaxy's evolution. Chemical and isotopic analysis would have been the most definitive way to determine Oumuamua's origin, as different star systems have subtle differences in their elemental abundances and isotope ratios. Unfortunately, Oumuamua was too faint and distant for such detailed spectroscopic analysis. The spectra that were obtained showed only broad colour information, insufficient to determine its detailed composition or compare it to known stellar populations. The possibility that Oumuamua might not have originated from any star system at all was also considered. Some theories of galaxy formation suggest that a population of free-floating objects might exist in interstellar space, formed in the early universe before the first stars, or ejected from globular clusters. These ancient wanderers would have no home star, having spent their entire existence drifting through the void. Statistical arguments suggested that Oumuamua was more likely to come from a relatively nearby star than from a distant one, simply because the density of such objects should decrease with distance from their sources. Most models indicated that the majority of interstellar objects in our neighbourhood should originate from stars within a few hundred light-years, though outliers from more distant sources would occasionally pass through. The type of star system that could produce an object like Oumuamua became a subject of intense theoretical investigation. Binary star systems, which make up about half of all star systems, are particularly efficient at ejecting objects into interstellar space. The gravitational perturbations from a companion star can destabilize the orbits of small bodies, sending them flying out of the system at high velocity. Red dwarf stars, which make up about 75% of all stars, were considered likely sources. These small cool stars are known to host planetary systems, and their lower escape velocities mean that objects can more easily be ejected into interstellar space. Additionally, red dwarfs are so numerous that statistically they should be the source of most interstellar objects. The possibility that Oumuamua came from a white dwarf system was particularly intriguing. White dwarfs are the remnants of sun-like stars that have exhausted their nuclear fuel and collapsed to Earth-sized objects of extraordinary density. The death throes of a star becoming a white dwarf could easily eject planetary material into interstellar space, and the unusual conditions might explain some of Oumuamua's strange properties. Young star systems in the process of forming planets were another probable source. During the early stages of planetary system formation, gravitational interactions between growing planets and smaller bodies result in a massive ejection of material. Models suggest that for every Earth mass of planets formed, several Earth masses of smaller bodies might be ejected into interstellar space. If Oumuamua was such a planetesimal, it would carry information about the planet formation process in another star system. The search for Oumuamua's origin also considered the galactic environment in which it formed. Different regions of the galaxy have different stellar densities, metallicities, and star formation histories. If Oumuamua formed in a dense stellar cluster, it might have been ejected by a close stellar encounter rather than planetary dynamics. If it formed in the galactic halo, it might have a very different composition than objects formed in the galactic disk. The role of molecular clouds in Oumuamua's history was another area of investigation. As the object travelled through interstellar space, it would have occasionally passed through the dense molecular clouds where stars form. These passages could have altered its surface composition through the accretion of dust and ice, potentially explaining some of its unusual properties. The molecular hydrogen ice theory explicitly invoked formation or modification in such clouds. Some researchers propose that Oumuamua might be a messenger from the early solar system, ejected billions of years ago and returning after a long journey through the galaxy. While the probability of such a return was extraordinarily small, it couldn't be completely ruled out. If true, Oumuamua would be a time capsule from our own system's youth, altered by its billions of years in interstellar space. The discovery of Oumuamua prompted a re-evaluation of how common interstellar objects should be. If the detection of one object implied a large population, as statistical arguments suggested, then the galaxy must be filled with the detritus of planetary formation. This interstellar flotsam would form a vast, invisible population, occasionally revealing itself when an object happens to pass close to a star with astronomers watching. The international response to Oumuamua's discovery represented one of the most intensive and coordinated observation campaigns in astronomical history. Within hours of the confirmation that this object was interstellar in origin, telescopes around the world were adjusting their schedules, cancelling planned observations, and turning their powerful eyes toward this rapidly departing visitor. The urgency was palpable. Every hour meant Oumuamua was moving farther away and growing fainter, and the astronomical community understood that this might be humanity's only chance to study an interstellar object up close. The Pan-STARRS telescope in Hawaii, which had made the initial discovery, continued to track Oumuamua in the days following its detection. The telescope's wide field of view and sensitive detectors made it ideal for following the object as it moved across the sky. Each night, weather permitting, Pan-STARRS would capture multiple images of Oumuamua, measuring its position with precision and monitoring its brightness. These observations were crucial for refining the object's orbit and detecting any changes in its appearance. The European Southern Observatory's Very Large Telescope in Chile brought its enormous light-gathering power to bear on Oumuamua. With mirrors 8 meters in diameter, the VLT could detect much fainter details than smaller telescopes. astronomers used various instruments on the VLT to study different aspects of the object. The 4S2 instrument obtained deep images and spectra, searching for any signs of cometary activity and attempting to determine the object's composition. The X-shooter spectrograph covered a wide range of wavelengths simultaneously, from ultraviolet through visible to near-infrared, providing the most comprehensive spectral coverage of Oumuamua. The Gemini Observatory, with telescopes in both Hawaii and Chile, coordinated observations to maximize coverage of Oumuamua. The Gemini North Telescope on Mauna Kea obtained some of the highest quality images of the object, while Gemini South in Chile continued observations when the object was not visible from the northern hemisphere. The two telescopes worked in concert, passing the baton of observation as Earth's rotation carried them in and out of view of Oumuamua. The Canada-France-Hawaii telescope on Mauna Kea contributed crucial observations in the early days after discovery. Its wide-field camera could track Oumuamua efficiently, while also monitoring a large area of surrounding sky for any signs of debris or companion objects. Though no such companions were found, these observations placed important constraints on scenarios involving fragmentation or binary systems. The Hubble Space Telescope's involvement marked a significant commitment of resources to studying Oumuamua. Hubble time is extremely valuable and usually scheduled months in advance, but the director granted special discretionary time for Oumuamua observations. Above Earth's atmosphere, Hubble could achieve sharper images and observe for longer periods without interruption from weather or daylight. Hubble's observations in January 2018 were among the last successful detections of Oumuamua before it faded from view. The Spitzer Space Telescope attempted to detect Oumuamua in infrared wavelengths, which would have provided crucial information about its size and thermal properties. Although Spitzer did not detect the object, this non-detection was scientifically valuable, placing upper limits on Oumuamua's size and constraining its possible compositions. The failure to detect thermal emission suggested that Oumuamua was either smaller than initially thought or had unusual thermal properties. Radio telescopes joined the observation campaign, searching for any signals that might indicate artificial origin or natural radio emissions. The Breakthrough Listen project used the Green Bank telescope in West Virginia to observe Oumuamua for 10 hours across 4 radio bands. The Allen Telescope Array in California also searched for signals. While no radio emissions were detected, these observations demonstrated the scientific community's willingness to test even unlikely hypotheses about Oumuamua's nature. The coordination of these observations required unprecedented international cooperation. The Minor Planet Center served as a clearinghouse for astrometric observations, collecting position measurements from observatories worldwide and computing updated orbital elements. The International Astronomical Union's telegram system rapidly disseminated new findings to the global astronomical community. Researchers shared data freely, understanding that time was of the essence. Data reduction and analysis proceeded in parallel with observations. Each telescope produced data in different formats, requiring specialized software and expertise to process. Images had to be calibrated, correcting for instrumental effects and atmospheric distortion. Spectra required careful extraction and wavelength calibration. The rapid fading of Oumuamua meant that many observations were at the limits of detection, requiring sophisticated techniques to extract meaningful signals from noise. The photometric observations measuring Oumuamua's brightness over time revealed the dramatic light curve that suggested its elongated shape. Different telescopes observed in different filters, providing colour information that helped constrain the object's surface properties. Combining observations from multiple telescopes required careful cross-calibration, accounting for differences in instruments and observing conditions. Spectroscopic observations proved particularly challenging due to Oumuamua's faintness. Long exposure times were needed to collect enough light for meaningful spectra, during which the object's motion across the sky had to be precisely tracked. The resulting spectra were often noisy and difficult to interpret, requiring careful analysis to distinguish real features from artifacts. The lack of strong spectral features itself became an important datum, constraining the object's possible compositions. The astrometric observations, measuring Oumuamua's precise position over time, were crucial for determining its orbit and detecting the non-gravitational acceleration. Each observatory contributed position measurements with carefully characterized uncertainties. Combining these measurements required accounting for systematic errors, differences in reference star catalogues, and the effects of Earth's motion. The detection of the small non-gravitational acceleration from these data represented a triumph of precise measurement and analysis. Weather played a crucial role in the observation campaign. Clouds, rain, and poor atmospheric conditions could render even the most powerful telescopes useless. The geographic distribution of observatories helped mitigate weather issues, as poor conditions at one site might be balanced by clear skies at another. Still, some critical observations were lost to weather, creating gaps in the coverage of Oumuamua's properties. The rapid fading of Oumuamua created a natural hierarchy in which telescopes could contribute. In the first weeks after discovery, moderate-sized telescopes could observe the object. By November, only large telescopes could detect it. By December, only the largest ground-based telescopes and Hubble could track it. This progression meant that different teams had to hand off observations as their telescopes reached their limits. The data management challenges were substantial. Each night of observation generated gigabytes or even terabytes of data that had to be stored, processed, and distributed. The rapid pace of the campaign meant that normal data processing pipelines had to be accelerated. Quick-look analyses were performed in near real time to guide subsequent observations, while more careful analyses continued for months after the observations ended. The discovery of Oumuamua resonated far beyond the astronomical community, capturing public imagination and sparking discussions that ranged from the nature of scientific inquiry to humanity's place in the cosmos. This first confirmed interstellar visitor became a cultural phenomenon, inspiring art, literature, and philosophical debates, while simultaneously advancing our scientific understanding of planetary systems and interstellar space. The impact of Oumuamua continues to influence how we search for and think about objects from beyond our solar system. The immediate public reaction to Oumuamua's discovery was one of wonder and excitement. Major news outlets around the world featured the story prominently, often leading with headlines about a mysterious visitor from another star system or alien object passing through solar system. While some of these headlines were sensationalized, they reflected genuine public fascination with the idea that we had detected something from outside our cosmic neighborhood. Social media platforms buzzed with discussions, artistic interpretations, and inevitable jokes about alien spacecraft. The scientific community's response was more measured but no less enthusiastic. The discovery validated decades of theoretical predictions about interstellar objects and opened an entirely new field of observational astronomy. Scientific journals fast-tracked papers about Oumuamua, recognizing the time-sensitive nature of the discovery. The first paper announcing the discovery appeared in Nature just weeks after detection, an unusually rapid publication for such a prestigious journal. Within a year, over 100 scientific papers about ʻOumuamua had been published, exploring every aspect of its properties and implications. The controversy surrounding Oumuamua's possible artificial origin brought unprecedented attention to the scientific process itself. The debate between Avi Loeb, advocating for considering the artificial hypothesis, and other astronomers who favoured natural explanations, played out not just in scientific journals, but in popular media. This public disagreement offered a window into how science actually works, showing that uncertainty and debate are not weaknesses, but essential parts of the scientific method. Educational institutions quickly incorporated Oumuamua into their curricula. From elementary school science classes to graduate-level astrophysics seminars, the interstellar visitor became a teaching tool for concepts ranging from orbital mechanics to the scientific method. Museums and planetariums developed special programs about Oumuamua, using it to explain everything from asteroid composition to the scale of interstellar distances. The object's Hawaiian name also provided opportunities to discuss indigenous astronomy and the role of Hawaii in modern astronomical research. The cultural impact extended into the arts, with Oumuamua inspiring numerous creative works. Science fiction authors incorporated the object into their stories, using it as everything from an alien probe to a generation ship to a harbinger of first contact. Musicians composed pieces inspired by Oumuamua's lonely journey through space. Visual artists created interpretations of what the object might look like, often emphasizing its reported elongated shape and tumbling motion. These artistic responses helped people emotionally connect with what might otherwise seem like an abstract astronomical discovery. The discovery influenced space policy and planning in subtle but important ways. Space agencies began considering missions to intercept future interstellar objects, recognizing that these visitors might provide unique opportunities to study material from other star systems. The European Space Agency studied a potential mission called Comet Interceptor that could be positioned to rapidly respond to a new interstellar object discovery. NASA examined whether existing spacecraft or planned missions could be adapted for interstellar object encounters. The search for extraterrestrial intelligence community took particular interest in Oumuamua, even though most SETI researchers did not believe it was artificial. The object demonstrated that we could detect interstellar visitors, raising questions about whether deliberate interstellar probes might be distinguishable from natural objects. Radio observations of Oumuamua, while yielding no signals, established protocols for how SETI observations should be conducted on future interstellar objects. The economic impact, while modest, was measurable. Telescope time devoted to Oumuamua observations represented millions of dollars in resources. Publishers saw increased sales of astronomy books and magazines featuring Oumuamua. Tourism to Hawaiian observatories experienced a small boost from people interested in seeing where the discovery was made. The object even influenced financial markets briefly, with some space-related stocks seeing movement based on speculation about its nature. Philosophically, Oumuamua prompted renewed discussion about humanity's cosmic significance. The confirmation that objects from other star systems pass through our solar system made the universe seem more connected, less compartmentalized into isolated stellar islands. Some saw Oumuamua as a reminder of our cosmic insignificance, a random piece of debris that happened to pass by. Others viewed it more optimistically, as evidence that the barriers between star systems are not insurmountable, that material, and perhaps even life, could spread throughout the galaxy. The discovery influenced how astronomers approach survey observations. The success of Pan-STARRS in detecting ʻOumuamua validated the importance of wide-field surveys that repeatedly scan the sky. Funding agencies became more receptive to proposals for new survey telescopes, recognizing their potential for unexpected discoveries. The Vera Rubin Observatory, set to begin operations in the mid-2020s, was designed with lessons from ʻOumuamua in mind, optimized to detect faint, fast-moving objects. International collaboration in astronomy was strengthened by the ʻOumuamua observation campaign. The rapid sharing of data and coordination of observations across multiple countries and institutions demonstrated the global nature of modern astronomy. This cooperation extended beyond professional astronomers to include amateur observers, some of whom contributed valuable observations during the brief window when ʻOumuamua was visible. The naming of ʻOumuamua had cultural impacts beyond astronomy. It introduced millions of people worldwide to a Hawaiian word and concept, promoting awareness of Hawaiian language and culture. The successful collaboration between astronomers and Hawaiian cultural experts in choosing the name provided a positive example of how Western science and indigenous knowledge can work together respectfully. This set a precedent for naming future discoveries in ways that honor local cultures and traditions. Public engagement with science increased measurably following ʻOumuamua's discovery. Science museums reported increased attendance at astronomy programs. Online astronomy courses saw enrollment spikes. Citizen science projects related to asteroid detection gained new participants. The object demonstrated that astronomical discoveries could still capture public imagination in an age of short attention spans and information overload. The discovery challenged and expanded our vocabulary for discussing cosmic phenomena. Terms like interstellar object, previously confined to technical literature, entered mainstream discourse. The designation system created for ʻOumuamua, with I for interstellar, established a new category of celestial objects. This linguistic evolution reflected and enabled new ways of thinking about our cosmic environment. The scientific legacy of ʻOumuamua extends far beyond the specific properties of this individual object, fundamentally altering our understanding of planetary system formation, the exchange of material between star systems, and the methods we use to detect and study celestial visitors. The lessons learned from this first confirmed interstellar object have reshaped theoretical models, observational strategies, and our conception of the solar system's relationship with the broader galaxy. These insights continue to influence astronomy years after ʻOumuamua disappeared from view. Perhaps the most fundamental lesson from ʻOumuamua concerns the abundance of interstellar objects. The detection of this single object, given the small volume of space monitored by our telescopes and the brief window when such objects are bright enough to detect, implies an enormous population of interstellar wanderers. Statistical analyses suggest that the galaxy contains roughly 10 to the power of 25 such objects per cubic parsec, meaning that at any given moment there should be about 10,000 interstellar objects within the orbit of Neptune, though most are too small or distant to detect with current technology. This abundance has profound implications for planetary formation theories. If star systems routinely eject such vast numbers of small bodies, the process of planet formation must be incredibly inefficient, with far more material expelled than incorporated into planets. The traditional view of planet formation as a relatively tidy process, with most material either accreting onto planets or remaining in stable orbits as asteroids and comets, requires revision. Instead, planetary systems appear to be cosmic fountains, spraying material into interstellar space throughout their formation and evolution. The extreme elongation of Oumuamua, if confirmed, challenges our understanding of how celestial bodies form and evolve. No formation mechanism easily explains a 10-to-1 axis ratio, suggesting either that our understanding of these mechanisms is incomplete, or that Oumuamua experience unique conditions not present in our solar system. This has prompted theoretical work on exotic formation scenarios, including tidal disruption, collisional fragments, and even the possibility that extreme shapes might be more common in other planetary systems with different formation conditions. The non-gravitational acceleration observed in Oumuamua revealed the limitations of our ability to characterize objects from limited observations. The fact that astronomers cannot definitively determine whether this acceleration was due to outgassing, radiation pressure, or some other mechanism highlights the challenges of studying objects we can only observe as points of light. This uncertainty has motivated development of new observational techniques and theoretical frameworks for interpreting ambiguous data. Oumuamua demonstrated the importance of rapid response in astronomy. The object was only observable for a few weeks before fading beyond detection, and much of what we learned came from observations made within days of discovery. This has led to changes in how observatories operate, with more emphasis on target of opportunity programs that can quickly redirect telescopes to observe unexpected discoveries. The success of the rapid response to Oumuamua has become a model for handling future transient events. The discovery highlighted gaps in our theoretical understanding of interstellar objects. Before Oumuamua, most models predicted that interstellar objects would be predominantly icy, resembling comets ejected from the outer regions of planetary systems. The apparently rocky or otherwise unusual nature of Oumuamua suggested that either these models were incomplete, or that selection effects meant he were more likely to detect atypical objects. This has prompted a re-evaluation of what types of objects planetary systems eject and what we should expect to observe. The role of selection effects in our detection of Oumuamua provided important lessons about observational astronomy. We detected this object because it passed relatively close to the Sun and Earth, was large enough to be visible, and happened to be discovered by our surveys. Understanding these selection effects is crucial for interpreting what Oumuamua tells us about the broader population of interstellar objects. The fact that we detected an object with such unusual properties might mean either that such objects are common or that we preferentially detect unusual objects. Oumuamua taught us about the importance of interdisciplinary collaboration in understanding cosmic phenomena. Explaining this object required input from planetary scientists, stellar astronomers, cosmologists, and even researchers studying artificial intelligence and extraterrestrial life. The breadth of expertise needed to fully investigate. Oumuamua demonstrated that traditional boundaries between astronomical subdisciplines are increasingly artificial and that major discoveries often require diverse perspectives. The controversy over Oumuamua's possible artificial origin, while ultimately unresolved, provided valuable lessons about how science handles extraordinary claims. The debate showed that the scientific community could seriously consider unconventional hypotheses while maintaining rigorous standards of evidence. It also demonstrated the importance of science communication, as public understanding of the debate varied widely depending on how media outlets presented the story. From a technical perspective, Oumuamua drove improvements in astronomical software and data processing. The need to quickly process and analyze observations of a rapidly moving, fading object pushed the limits of existing pipelines. Software developers created new tools for trajectory calculation, light curve analysis, and spectral extraction optimized for faint moving targets. These improvements benefit not just interstellar object research, but many areas of time-domain astronomy. The discovery influenced mission planning for future space exploration. The possibility of studying material from another star system without the need for interstellar travel has obvious appeal. Several space agencies have studied concepts for missions that could intercept future interstellar objects, either with flyby spacecraft or even sample return missions. While technically challenging, Such missions are far more feasible than interstellar probes and could provide unprecedented insights into other planetary systems. ʻOumuamua revealed the importance of having diverse observational capabilities. Different telescopes contributed different pieces of the puzzle. Optical telescopes measured position and brightness. Infrared telescopes searched for thermal emission. Radio telescopes checked for artificial signals, and spectroscopic observations attempted to determine composition. The complementary nature of these observations demonstrated the value of maintaining a diverse ecosystem of astronomical instruments. The object taught us about the limits of remote sensing in astronomy. Despite observations with the world's most powerful telescopes, fundamental questions about Oumuamua's size, shape, composition, and nature remain unanswered. This uncertainty is humbling, reminding us that even with sophisticated technology, there are limits to what we can learn about objects we cannot directly sample or visit. It underscores the value of sample return missions and in situ exploration for solar system objects we can reach. The discovery prompted new thinking about the early solar system and the possibility that Earth might have been influenced by interstellar visitors. If interstellar objects are as common as Oumuamua implies, Earth has likely experienced numerous impacts from such objects over its history. These impacts could have delivered exotic materials or even organic compounds from other star systems, adding another dimension to theories about the origin of life and the chemical evolution of planets. Oumuamua demonstrated the predictive power of theoretical astrophysics. The existence of interstellar objects had been predicted decades before one was observed, based on models of planetary system formation and dynamics. The successful prediction and subsequent discovery validated these theoretical frameworks, while also revealing their limitations. This interplay between theory and observation exemplifies how astronomical understanding advances. The discovery of Oumuamua marked not an end but a beginning, the opening of a new era in astronomy, where interstellar objects would transition from theoretical constructs to observable targets. The lessons learned from this first detection have shaped plans for future surveys, influenced telescope design, and motivated development of rapid response protocols for when the next interstellar visitor is discovered. The future of interstellar object detection promises to transform our understanding of planetary systems throughout the galaxy and our place within the cosmic ecosystem. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, represents the next generation of survey capability that will revolutionize interstellar object detection. Set to begin operations in the mid-2020s, this observatory will photograph the entire visible sky every few nights with a camera containing 3.2 billion pixels. Its unprecedented combination of aperture size, field of view, and survey cadence means it should detect interstellar objects much fainter and more distant than Oumuamua, potentially finding several such objects per year. The capabilities of the Rubin Observatory will allow astronomers to detect interstellar objects earlier in their approach to the inner solar system, providing more time for detailed study. Where Oumuamua was discovered only after its closest approach to the Sun, future discoveries might come months or even years before perihelion, allowing for comprehensive observation campaigns and potentially even missions to intercept these visitors. The extended observation window will enable studies of how these objects behave as they warm approaching the Sun, potentially revealing cometary activity invisible at larger distances. Improvements in computational capabilities and machine learning algorithms will play a crucial role in future interstellar object detection. The volume of data generated by next-generation surveys will be too large for traditional analysis methods, requiring artificial intelligence systems to identify potential interstellar objects among millions of observations. These systems are being trained on simulated data and the characteristics of Oumuamua to recognize the subtle signatures that distinguish interstellar from solar system objects. The discovery of a second interstellar object, 2I Borisov, in 2019 provided validation that Oumuamua was not a unique event and offered a contrasting example of what interstellar visitors might look like. Unlike the enigmatic ʻOumuamua, Borisov was clearly a comet, displaying obvious outgassing and a prominent tail. This diversity in just the first two detected interstellar objects suggests that future discoveries will reveal a wide range of compositions, origins, and behaviours. Space-based telescopes will increasingly contribute to interstellar object detection and characterization. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will have the ability to detect extremely faint objects and could potentially discover interstellar objects in the outer solar system, far from the Sun. The James Webb Space Telescope, while not optimized for moving object detection, can provide unparalleled spectroscopic observations of discovered interstellar objects, potentially determining their compositions with far greater precision than was possible for ʻOumuamua. The possibility of intercepting an interstellar object with a spacecraft has motivated serious mission studies. The European Space Agency's Comet Interceptor mission, approved for launch in the late 2020s, will wait at the Sun-Earth L2 Lagrange point for a suitable target, either a long-period comet or an interstellar object. When such a target is discovered, the spacecraft would be dispatched for a high-speed flyby, providing close-up images and in-situ measurements impossible from Earth-based observations. More ambitious concepts for interstellar object missions are being developed. Some proposals involve spacecraft with high-performance propulsion systems that could chase down an interstellar object even after it has passed through the inner solar system. Others suggest pre-positioning multiple small spacecraft throughout the solar system, ready to intercept objects approaching from any direction. While technically challenging and expensive, such missions could provide transformative science, essentially bringing samples from other star systems within our reach. The detection of interstellar objects will benefit from improved international cooperation and data-sharing protocols. The experience with ʻOumuamua showed the importance of rapid communication and coordination among observatories worldwide. Future discovery protocols will likely include automated alert systems that immediately notify relevant telescopes and spacecraft when a potential interstellar object is detected, maximizing the scientific return from these brief encounters. Amateur astronomers will play an increasing role in monitoring interstellar objects. While discovering such objects requires large telescopes, once detected, some interstellar visitors might be bright enough for amateur equipment to track. Networks of amateur observers could provide continuous monitoring, filling gaps in professional observations and potentially detecting brightness variations or outbursts that might be missed by less frequent professional observations. The search for interstellar objects will expand beyond visible light observations. Radio telescopes will routinely check new discoveries for artificial signals, maintaining scientific rigor while acknowledging public interest in the possibility of alien artifacts. Gravitational wave detectors, while not directly detecting small objects, might identify massive interstellar visitors or the effects of dense objects passing through the solar system. Neutrino telescopes could potentially detect exotic physics associated with unusual interstellar objects. Theoretical work will continue to refine predictions about the population of interstellar objects. As more objects are discovered, statistical models will improve, allowing better estimates of the total population, size distribution, and composition range of interstellar visitors. These models will guide observation strategies and help identify which objects are most scientifically valuable for detailed study or spacecraft missions. The possibility of capturing an interstellar object into orbit around the Sun, while extremely unlikely to occur naturally, has been studied as a potential future capability. If an interstellar object could be detected far enough in advance, a spacecraft might be able to alter its trajectory slightly, capturing it into a bound orbit where it could be studied indefinitely. While beyond current technology, such capability might be achievable in coming decades. Future discoveries will likely include interstellar objects of types not yet imagined. Just as ʻOumuamua surprised astronomers with its unusual properties, future visitors might challenge our understanding in new ways. We might discover interstellar planets, ejected from their birth systems and wandering through space. We might find objects composed of exotic materials, formed under conditions unlike anything in our solar system. Each discovery will expand our understanding of what is possible in the universe. The study of interstellar objects will increasingly connect with other areas of astronomy. As we discover more exoplanets and learn about the architecture of other planetary systems, we can better understand what types of objects they might eject. Conversely, the interstellar objects we detect provide ground truth for models of planetary system evolution. This synergy between different observational approaches will provide a more complete picture of planetary systems throughout the galaxy. The cultural impact of future interstellar object discoveries will depend partly on their nature. Another ʻOumuamua-like object with mysterious properties would likely generate enormous public interest and scientific debate. A clearly natural object like Borisov might receive less attention but could be more scientifically valuable for understanding typical interstellar material. The discovery of an object with unambiguous signs of artificial origin would be one of the most significant events in human history. Educational and outreach programs are being developed to help the public understand and engage with interstellar object discoveries. These programs emphasize not just the objects themselves, but the scientific process of discovery and investigation. By involving the public in the excitement of these discoveries, astronomers hope to inspire the next generation of scientists and maintain support for astronomical research. The legal and policy framework for dealing with interstellar objects is still evolving. Questions about planetary protection, the handling of potentially hazardous objects, and even ownership of intercepted interstellar material need to be addressed. International agreements may be needed to ensure that the scientific investigation of interstellar objects proceeds cooperatively rather than competitively. As detection capabilities improve, we may begin to discover interstellar objects while they are still in the outer solar system, years before they approach the Sun. This extended warning time would fundamentally change how we study these visitors. Instead of the frantic few weeks of observation possible with ʻOumuamua, astronomers would have years to plan comprehensive observation campaigns, potentially even launching dedicated missions to intercept these objects. The scientific return from such extended study would be immeasurable, allowing us to watch how interstellar objects respond to solar heating, search for outgassing at various distances, and monitor any changes in rotation or structure. The next decade will likely see the establishment of dedicated interstellar object survey programs. While current surveys discover these objects, incidentally, while searching for asteroids and comets, future programs might be optimized specifically for interstellar object detection. These could include telescopes positioned at high solar latitudes to better detect objects approaching from above or below the ecliptic plane, or networks of small telescopes providing continuous all-sky coverage to ensure no visitor goes unnoticed. Advances in telescope technology will dramatically expand our ability to characterize interstellar objects. Adaptive optics systems are becoming increasingly sophisticated, allowing ground-based telescopes to achieve near space-based resolution. The extremely large telescopes currently under construction, with mirrors 30 to 40 meters in diameter, will be able to detect the faintest whispers of light from distant interstellar visitors, and potentially even resolve the largest ones as more than points of light. These capabilities will allow detailed spectroscopic studies that were impossible with ʻOumuamua. The development of quantum sensors and other exotic detection technologies might reveal aspects of interstellar objects invisible to traditional telescopes. Quantum interference techniques could potentially detect extremely small variations in gravitational fields, identifying dense interstellar objects that might otherwise go unnoticed. Advanced polarimetry might reveal subtle surface properties that distinguish interstellar from solar system objects. These emerging technologies could open entirely new windows for studying interstellar visitors. The integration of interstellar object detection with planetary defense systems will become increasingly important. While the probability of a hazardous impact from an interstellar object is extremely low, The high velocities of these objects mean they would carry enormous kinetic energy. Planetary defense surveys will need to account for the possibility of interstellar impactors approaching from unusual directions at higher speeds than typical solar system objects. This integration will require new protocols and response strategies tailored to the unique challenges of interstellar threats. Future discoveries will likely reveal patterns in the properties of interstellar objects that inform our understanding of planetary system formation throughout the galaxy. Do most star systems eject similar types of objects, or is there wide diversity? Are there correlations between the properties of interstellar objects and the types of stars they come from? As our sample size grows from the current 2 objects to dozens or hundreds, statistical patterns will emerge that reveal universal principles of planetary system evolution. The possibility of discovering interstellar objects with clear biosignatures, while remote, cannot be ignored. If life exists elsewhere in the galaxy, the material ejected from living worlds might carry chemical or isotopic signatures of biological processes. While distinguishing such signatures from abiotic processes would be challenging, the discovery of clearly biological material in an interstellar object would revolutionize our understanding of life's distribution in the universe.